Welcome to the 6th lecture, and we'll be continuing on chapter 4 of CLRS, which is the general topic of divide and conquer algorithms. To start with, let's take a quick look at where we are in the course. And we generally on the topic of divide and conquer algorithms, and we started off by looking at an example of a divide and conquer algorithm, which was merge sort. And then we looked at how one could prove that the algorithm actually works, and we used the loop invariants for showing the proof of correctness. And then when we tried to analyze it, we came across a recurrence relation, right? And we said, well, there are several ways to solve recurrence relations. We looked at recursion tree method, which was sort of the most intuitive, I suppose, most graphical way. And then we looked at the substitution method, quite a mathematical way. And then finally, we looked at master method, which we started off in the last lecture, and that's where we'll be continuing. And hopefully, we'll also take a look at another example besides merge sort of a divide and conquer algorithm, and that is called the Strassen's matrix multiplication. Okay, it uses the divide and conquer on matrix multiplication. And hopefully, if you're done with that today, I will start the next major section of CLRS, which is a probabilistic analysis. And we'll also look at, besides looking at situations which are handled by a probabilistic analysis, which means that perhaps, let's say, when we're doing averages, as I mentioned, when you're doing averages, you need to have some kind of a distribution, an idea of the distribution of the input. Okay, and that's where probabilistic analysis comes in. But there's also another class of algorithms which are referred to as randomized algorithms. Okay, and before we get into that, we will also take a look at just reviewing probability, the basics of probability as well. So let's continue on with the master method. And in the last lecture, we had reviewed the master method, which I said is essentially a cookbook approach where you simply look up. But it's also good to know, have an understanding of where you can apply. So you can just take a look at maybe a recurrence relation, and you should be able to guess, well, which one of the three categories, which one of the three cases does this apply to, okay? And we looked at various ways of trying to understand them. So the first one, and I've changed the order now to be in line with the case numbers. So the first case is the one where the problem gets harder, okay? And this was the example where we saw that if you're starting off with, let's say, A is equal to 3 and B is equal to 2, so you can see that you're essentially making the problem harder as you're going down, right? As you're dividing and conquering. So you're going from 8C to 27C. And so the work is being done right at the bottom where the leaves are. And so this is the complexity is given by the following equation, which sort of represents, and I haven't showed a proof of this yet, but without going into all the details, you can use this, what is referred to as a watershed function, which is basically n to the power log to the base b of a. And that essentially gives you the complexity right at the bottom, okay? And we looked at an example where the number log b to the log to the base b of a, sort of how you can relate to that in different examples. The second case was where you had the cases being, as you divide and conquer, it becomes evenly distributed, okay? And this was the case with merge sort. And you saw that in this case, the complexity of the problem is not really changing as you divide and conquer, okay? And in this case, perhaps the complexity is given by a slightly more complex equation, and that's given by not just the watershed function, which is n to the power log b of a, log to the base b of a, but also it also has a multiplication with some power of log of n, log to the base b of n, okay? And we'll take a look at, and this was the example where we where we started off with, where we looked at merge sort and was basically n log n. Okay, and so this in a general setting comes out to be this slightly more complex situation. The function, which we'll see, becomes slightly more complex as we go forward. The third case was where the problem becomes easier. Okay, and this was given by an example: a is equal to 2 and b is equal to 3, where you're dividing it up into two subproblems, but each one of them are 1/3 the size of the original problem. Okay, so you can see that the problem is becoming easier as we're going down, and so most of the work is being done at the root level. And so you can imagine that the complexity is essentially given by the function f of n over here. Okay, and the other way of looking at this, I can somehow get rid of this popping up. It didn't used to happen like this in the past. For some reason it keeps popping up. Okay, so another way of looking at the master method is, as I showed you earlier, that you have a driving function. So this f of n is referred to as a driving function, and then you have the watershed function. Okay, and that's n to the power of log to the base b of a, and you're basically comparing the complexity of the driving function with respect to the watershed function. Okay, so if the driving function f of n grows slower than the watershed function, then the first case applies. Okay, so the driving function is slower than the watershed function, and so this is the first case where basically if the driving function is slower, then essentially the problem is getting harder, and so we're not really using the driving function in order to drive the result. Okay, and that's the first case. And the third case, the second case is sort of in the middle, and the third case is where the driving function is more complex than the watershed function. In which case, the third case applies. Okay, and you can sort of relate to it now in the more detailed theorem. So you can see that the watershed function is actually slower than the driving function is slower than the watershed function. This was the first case. Okay, driving function is slower. And why is that? Because you can see the watershed function over here. Okay, and there is a minus epsilon, which is indicating that now the driving function is slightly slower, or it could be substantially slower than the watershed function. Okay, in which case basically all the work is being done at the bottom, and that is given by this. The complexity is given by this equation. And the third case is where you can see that there is the watershed function has a plus epsilon. Okay, and that is the case where the driving function is a little faster. Okay, a little or a lot faster, but has to be faster. It can't be equal. Okay, so this is the first case is the driving function is less in complexity. This is the case where it's more in complexity, and this is the case which is in the middle, which is not exactly. You can't really say. You can't exactly relate it to these two situations, but in this case, you essentially saying that the driving function also has a log. So not just the watershed function, but it also has a log term to it. Okay, and we saw, if you can again relate it to the merge sort, where you saw that the height of the tree has a log term in it, and you're multiplying it before you actually get the driving function. Okay, and so and then now we have a more generalized solution for this in the master theorem, where you can say, well, it could have some power of k. Okay, so initially in the merge sort, the power of k was actually 0, but the complexity had power of log in it. Okay? So let's take a look at, so this was sort of a summary of it. You can refer to this as we go forward. And we looked at different examples in the past, in the last lecture. And so let's take a look. So in all of these cases, this is all basically the case 1. And in case 1, remember that the driving function is slower than the watershed function. Okay, so you can see that the driving function has lower power than the watershed function, which is 0.49999. All right, as long as it's slightly, as long as it's less than 0.5, basically the complexity is going to depend on the watershed function. Okay, it will not depend on it has no connection. It doesn't depend at all on f of n. Okay, so as long as f of n in all of these cases, you notice that I've picked log to the base b of a to be increasing value as long as the driving function has a power which is less than the log of a. Okay, so you can see that I've chosen any values from 0 to 1.9, and the complexity is basically based on log to the base b of a. Okay, so this was the first case, and let's go on and look at some examples of the second case and see if you can make sense of this. So here's another example where I've got a is equal to 2 and b is equal to 4. Now, towards the end of this of the previous lecture, I sort of started this perhaps, and I said, well, if b is 4 and a is equal to 2, what does that immediately indicate to you? Is the problem getting harder or easier? You're dividing it up into two parts, but each of those parts is actually 1/4 in size. So is the problem becoming harder or easier? It's becoming easier, right? So you would think that if we go back to our original point, that if it's becoming easier, it should have been case 3. Okay. So so we have to take this particular slide with a grain of salt, and you have to understand that the real complexity, the real theorem, is that you actually have to compare these two functions. So you can't just take a look at, and those were good to start with, but you can't just say that if the problems become easier or harder, you have to compare it with the f of n function. Okay, that's the ultimate criteria, and that's what is being given in the theorem, right? So if you're comparing it now with the driving function, now you can see that in fact this is not the third case, but this is in fact the second case. Why is that? Because I've chosen f of n to be n to the power 0.5, and these two are exactly matching. Okay, so if these two are exactly matching, and you have you can see that in this case there is log to the power 0 of n can be invisibly seen to be there. So you can see that this is the case 2, where essentially k is equal to 0. Okay, because anything to the power 0 is 1. So you can see that this is a case 2, where these two are essentially equal, and your log is not really there, but it's essentially the power of 0. Okay, so in that case, your complexity is essentially given by your watershed function, but you also have if you look at the previous theorem, it says that you also have log to the power of k plus 1. Okay, so if f of n has a log to the power of k, then your complexity will have a k plus 1 in it. Okay, so a little tricky, but hopefully if you see enough examples of this, you should be able to figure this out. So let's take a look at another example. And here what I'm saying is that, again, these two are the same. Okay, and however, you have in the f function, the driving function, you have a logarithm, a log present. Okay, we haven't seen an example, a real algorithm which relates to this, but let's say hypothetically you had a real example, a real algorithm which had this function. Okay, so could you solve it using the master method? And what would be the answer? So first of all, what's k in this case? Okay, so just take a look at this. You've got the driving function has to be of this form, and k is given by, yeah, k is given by 1. So you have 1 over here, and so the solution is really nice. It just pops out. Okay, so you just take k plus 1, and this is what your solution is. So this is it just gives you the complexity. You don't really have to put too much effort into it. So let's take a look at yet another example. So now we have 2 and 2. Okay, so you're dividing it up into two smaller problems. Each one of them are half in size. And I'm assuming that log to the power 0 of n, everybody knows that is. So this basically the complexity is simply theta of n. What does this remind you of? Which particular problem does this remind you of? Sorry? Merge sort? Yeah. So we've seen that enough times to be able to recognize it by now. And so we should know, well, what is k in this case? K is clearly 0. And so the answer, we already know what that is. And you can see that the master theorem sort of, makes, it confirms the lengthy process by which we derived this. And that just simply gives you the answer. So you can see more examples of this as long as you have the driving function of this particular form, okay? And your these two values are matching. Okay, so remember this has to match over here. So the driving function must have the power of n, not the log power, but the power of n has to match with the watershed function. Okay, so you can see that in all of these cases, these two powers are in fact coinciding. I've just picked the functions f of n which happen to coincide and which have some log of n as well. And if you have log to the power of 1 over here, then you simply increment it. Okay, that's why it's called a Cook solution, because you just, as long as you can recognize which case it is, you're okay. Okay, you're good to go. So let's take a look at the third case. What is B again? The question. Okay, so remember B is right up here. Okay, so you have your recurrence relation, which says you're taking up your original problem T. I'm not sure when that question came, but just answering it at this moment. So you have A and B over here, which are part of the recurrence relation. Okay, so let's take a look at the third case. The third case is where your driving function is actually higher in complexity as compared to your watershed function. Okay, and do note that we sort of neglecting this, but you do have a big O and a big omega somewhere in that equation as well. Okay, so and then in case 3, you must have this function f of n must also satisfy an additional requirement. Okay, so that's always important. Whenever you do apply case 3, you must make sure that the regularity condition is also met. Although, as I said, in most cases it does meet it, but if you are given a problem recurrence relation and you didn't check this, it's quite possible that you might come down to a wrong answer. So let's take a look at an example of this. So you can immediately see that the driving function has a power which is higher than that of the watershed function. Here it's 0.5, now it's 0.6, and epsilon is simply the difference of the two. And so in this particular case, because the complexity of the driving function is higher, then now all the work is being done right at the top. And so the complexity simply depends on the driving function itself. Okay, so this is not really helping. And so you can simply show that the complexity is based on f of n. Okay. So let's take a look at this example. By now, hopefully it should be fairly clear. What's epsilon over here? Epsilon 2.5. And what would be theta? N to the power of. So it would depend on f of n. Okay. So it would be theta of n cube. All right. It simply depends on f of n. Okay. Whenever, if f of n has higher complexity, it's sort of almost now becoming part of intuition that you can just pick this up. Okay. So again, I have a whole bunch of examples, and I'm not going to belabor this, but you can see that in all of these cases, again, this is with different values of a and b. Log to the base b of a comes out to be 1. And so if it is 1, then you could pick f of n to be any power higher than 1. So 1.1, 3, 100 million, whatever. In all of these cases, essentially this function over here is going to determine the complexity. Okay, similarly over here, we've got a and b to be 4 and 2. So log to the base b of a is now 2. So as long as f of n has a power which is greater than 2, whether it's 2.1 or 3, you calculate your epsilon just for reference, and then you simply pick this function that's going to determine the complexity. Okay, so hopefully by now you should be able to, look at a recurrence equation and sort of, be able to say what the result is without actually having to look at this particular, you don't necessarily have to look at this by now. So if you've seen enough of examples, you should be able to just make sure that you can intuitively give the result. However, just make sure that the regularity condition is also met. So let's take a look at what the regularity condition is implying. So let's take a look at an example of the regularity condition. So here, basically, essentially, we're saying is that we need to make sure that the function f of n is sort of well behaved. Okay, how are we defining that? We're essentially saying that a, so we're using the a and the b, okay, from the recurrence relation, and we're saying that if you divided up the problem into a smaller problems, into a problems, and each one of them is smaller by b, by a factor of b, then that has to be less than some constant times the original function. Okay, I don't know if you can sort of give an intuition to that equation, but and c has to be less than 1. Okay, so it has to be smaller than the original function. So let's take a look at this. This was, I'm just picking out one of the examples. So if you plug the numbers in, what do you get? And let's take a look at this. So you're basically saying a is equal to 2 over here, and b is equal to 4. So 2, and the function f of n is n squared. So we're saying that 2 times n divided by 4, the whole squared, because we have the function is n squared, has to be less than equal to c times the function f of n, which is n squared, and c has to be less than 1. Okay, so you can clearly see that this becomes 16 times, and 2 cancels out, so that becomes 8. And so n squared cancels out, and you essentially have 1a less than equal to c, which has to be less than equal to 1, less than 1. Okay, and you can see that that's true. You can find a value of c which satisfies this equation. So the regularity condition has been met over here. All right. So that's the master method, and we've hopefully given you a reasonable understanding of what that is. And so that sort of concludes the three broad methods that we've talked about to solve recurrence relations. Okay. So let's go on to the next major topic. Well, not major topic, but next example of a divide and conquer algorithm, which is called the Strassen's algorithm. And basically, it's based on matrix multiplication. Okay, so let's take a look at matrix multiplication. So hopefully, everybody remembers what how we do matrix multiplication. So if in case somebody's forgotten, this tells you if you have a 2 by 2 matrix, how do we do it? Well, we take A and B and multiply it by E and G, and that's how you get the first entry over here. And then we take A and B multiplied by F and H, and you get the second column of the first row, and so on. Okay. And similarly, if you have the first row and you multiply it by the first column, and that's how you get the first element of the matrix that we multiplied. Okay, so nothing new so far. Okay, now the question is, can we apply a divide and conquer solving this? So has anybody seen this approach? I mean, have you come across being able to apply a divide and conquer method to matrix multiplication? How many of you have seen that, come across that? Somebody nodded over there in the middle. Yes. So can you explain to me how would you actually apply divide and conquer? Yeah, that's true. But let's just and you're absolutely right, and that's why we're studying this algorithm. But let's just take a look at the basic matrix multiplication, and the question is, can you divide up this problem into a divide and conquer category? Yes, please. Which are sorry? Yes. So far we are assuming that they're perfect squares. Okay. And just to make it simple, but it doesn't necessarily have to apply to those cases. And if they're not perfect squares, you can sort of pad them up and put zeros and stuff like that and still make it work. Okay. But let's start with the simple example where they are perfect squares, and there is something in 2 to the power n. So 4, 16, and so on. So the basic question is, can you divide this problem up into the divide and conquer paradigm? Okay. Can somebody give me a way of dividing them? Yes. Okay, so great idea. Can I get your name? Brenda. Okay, so Brenda's suggestion is that we take both of the matrices, right? And you divide it up into, we halve them, is that right? Okay, so we halve both of these, and now we've got 4 smaller matrices, each of 1/4 of the size. Okay, but let's assume that this is n. This is an n by n matrix. Okay, so this is now an n by 2 by n by 2 matrix, right? And now what do we do? Brenda? Yeah. Okay. Okay, very good. So Brenda's suggestion is that you simply take this, and what you can do is you can treat these blocks as, just like a 2 by 2 matrix, but instead of each one of these sub blocks being a single element of a 2 by 2 matrix, it's actually an entire matrix by itself. Okay, and this is quite an interesting strategy, and normally you don't come across this in most linear algebra courses, but this is in fact true. You can check it out. This actually works out. So you can make this A, and so you can take A multiplied by E. Okay, so you take A times E, and B times G. Okay, and if you did the multiplication and you added them up, you should be able to get it. Okay, and you would be able to just get the top left quadrant. All right, and similarly, if you want to get this particular quadrant, all you have to do is take, B, in this case, it would be A times F over here and B times H. Okay, and you can proceed. So great. And this is sort of a worked out example just to show you that, in fact, this is true. I've taken some numbers and sort of multiplied them up. So it seems to be doing maybe a lot more work than the original problem. And the question is this really helping? Does your intuition tell you that are we sort of breaking into? At the end of the day, are we actually a real, divide and conquer algorithm, which actually helps rather than makes things worse or makes it about the same? If you look at the amount of work being done, we're taking these smaller matrices, multiplying it together, and now you have one matrix multiplication, and then an additional addition. Okay, addition of matrices. So does and you have every submatrix. Okay, so you have to repeat this for here, for this, and so on. Okay, so let's get your intuition to work out. Do you think this is making the complexity better, the same, or worse? Now, you have in the back of your mind that we're talking about a new algorithm, so it couldn't be making it worse. But what about, is it making it better or not? Yeah. Yes. So how many multiplications would we have to do? How many matrix multiplication would we have to do? And if you think about your recurrence relation, what would your recurrence relation look like? So let's say you had an original equation T of n, and you had Tn upon B plus theta of some function f of n. So can somebody tell me what would A be, what would B be, and perhaps what would f of n be? So B, you're thinking would be 4, and A, 4 as well. Okay. So how many of you agree or disagree? Or don't have a clue? So anybody agrees or disagrees? So how many matrix multiplications would you have to do? And are we dividing it up into, so I just said earlier that we're going to assume n to be equal to not the entire number of elements in the matrix, but just one side, okay? So this is an n by n matrix, and now we've divided up into an n by 2 matrix. So your name once more, and I'll try to remember this time. Lasia? Okay, good. So Lasia, can you suggest, would you like to revise your values for A and B based on what I've just said? Okay, so Lasia thinks that B might be 2. Is that what you're saying? And A is still going to be 4. All right, so any other thoughts? Just try to do the matrix multiplication in your head. Okay, just look at this equation. So this looks good. All right, so let me just confirm what seems to be right. Okay, so you are dividing up the problem into a smaller problem, which is now, if you look at this matrix multiplication, this is basically n has become halved, right? So we agree on that. But what about A? So you're saying that there are 4, if you divide up that problem into 4 smaller problems. I'm sort of giving you a hint that that might not be right. Okay. So think about how we're dividing up the problem. Are we really dividing up into small? So it's a little complicated right now because the question is, what is A? Okay, is that the number of additions? Is that the number of multiplications? So it's not clear because now you divide it up into a smaller problem, which has a whole bunch of things in it. Okay, so it's got multiplication. So A times E, that's multiplication over here. All right, but then it also has an addition. It's not exactly clear what A is referring to. Okay, is A referring to just the multiplication part, or is it also referring to the addition part? And so now I want your thoughts as well. So what do you think it should refer to? Should it just refer to the multiplication, or should it include the additions as well? And let's focus on one thing at a time. So let's take a look at the multiplications. How many, if I just say in terms of multiplications, how many multiplications are now being performed? And last year saying 4, but not so sure anymore. How many multiplications are being performed? 8. Okay, can I get your name? Brand. Okay, so 8 multiplications, and I think you can see where those are. A times E plus B times G, that's the second one, third, fourth, fifth, sixth, seventh, 8. Very good. So we have 8 multiplications, not 4. Okay, does everybody agree to that? Okay. Yes, no? Hopefully you can see that there are 8 multiplications of smaller matrices. Okay, but then what about the additions? And should we include the additions in terms of the complexity, or should we disregard them? Okay, and should the additions be sort of come in over here, or should they come in over here? So to be able to write a recurrence relation is also often tricky. Okay, so you have to look at all of these aspects when you come across a new problem. Can you really convert it into a recurrence relation? Okay. So any thoughts? No clue. Okay. So let's take a look and see how we can proceed with this. Okay. So if you look at multiplication, what's the complexity of multiplication as compared to addition? Okay. So let's say you have an n by n matrix. Okay. What is the complexity of multiplication, and how does that compare to addition? So if you try to calculate an individual element of C, and if this has n elements here and n elements here, what's the complexity of just calculating a single element of C? Is that order of n, order of n squared, order of n cubed, order of n log n? It's fairly straightforward. So what are we doing over here? We're doing 1 times 5 plus 2 times 4 and so on. Okay, so the question is, what's the complexity? So if you look at the total number of, so if you look at 1 times 5, that's a multiplication that doesn't really depend on n, right? What does depend on n is the number of rows or columns. Okay, so what's the complexity of calculating the number 30 in terms of n? Yeah, so it's just order of n. Okay, so theta of n is the complexity of just calculating one element of the C matrix. And how many elements do you have in the C matrix? N squared. So the total complexity of multiplying the entire matrix is n cubed. Okay, so we come out with theta of n cubed. All right, what about addition? So if you want me to remind you what addition is, what you do is you basically say 1 plus 5. So if you multiply, adding a plus b, you're simply saying 1 plus 5 over here, and so on. Okay, so 1 plus 5 as a complexity, does it depend on n? No. So what's the complexity in terms of n for addition? N squared. Okay. So that should be n squared. So hopefully everybody can see that. Okay. So the complexity of multiplication is certainly higher than addition. Okay. So now if you go back to our original question, what do you think is the recursion relation between this? Okay. So what do you think now A should be? And should it depend on the multiplications, or should it also depend on the additions? And where and what should f of n be? So what should A be? Should depend on the number of additions or multiplications. Well, if you look at the number of additions, those are proportional to n squared, and the number of multiplications are proportional to n cubed. Okay, so if you look at how we're dividing up the problem, the complexity of the problem, hopefully you should be able to see that this is, it's going to depend on the number of multiplications, because that's more complex. Okay, and we're dividing it up into 8 multiplications. Okay, we saw that earlier. So this is the number of the complexity of the smaller problem in terms of its most complex aspect. Okay, so we've divided up into 8 smaller problems, each one of them being half in size. Okay, so if I were to draw a recursion tree, what would that look like? How many sub branches would it have? 8. Okay, so you'd have, it's what is called a very bushy tree. Okay, so you've got 1, 2, 3, 4, 5, 6, 7, and 8. Sort of like on those spiders. Okay, so so this is a bushy tree, and it's got 8 subdivisions, and each one of them are only half the size. Okay, each one of them are only half the size, so we've only divided up into or n by 2. Okay, so the question is, are we really getting anything out of it? So what do you have to compare? Okay, so how, if you remember your if you compare it back, think about your either your master theorem, or if you can think about it in any one of those 3 techniques that we talked about solving a recurrence relation, which one would be the easiest to use now? So would you want to do it in terms of, well, this would be, doing a recursion tree would take a little bit of time, okay, perhaps more time. If you did the second method, which was substitution, again, it might take a bit of time. But if you use the master method, can you just look at the equation and come up with a solution? Okay, so f of n in this particular case would be what? How much time are we taking up either to divide the problem or to recombine the problem? Okay, so let's talk about dividing the problem first, and then we'll talk about combining. So how much time are you taking to divide the problem? Yes. Yeah. Okay, so why B is 2? So we're basically saying that B is the size of the matrix on each side. Okay, if you're saying that this is a 4x4 matrix, n is not 16, n is 4. That's how we're defining the problem. Okay, so n is the size, the number of rows or the number of columns, and we're assuming that they're both the same. It's a square matrix, so n is given by the number of rows or columns. And so if you're using a divide and conquer approach, you basically, what you're doing is you're dividing it up into 4 smaller matrices. Okay, and each one of them are of side, this size is now n upon 2, okay, and this is n upon 2. And so now each one of these smaller matrices are n by 2 times n by 2. Okay, so essentially you've divided up the problem into a smaller problem. And if the original problem was of size n, now the smaller problem is of size n by 2. Okay, so so that explains B. And is anybody still confused about why A is 8? Okay, So hopefully that's clear. So now if A is 8, B is 2, what is f of n? Okay, so f of n, remember, is the amount of time taken to either divide or recombine. So let's think about the amount of time to divide the problem. How much time is being taken? Does it depend on n? Okay, so you're sort of assuming how you're actually implementing the algorithm. And the question is, if you implement the algorithm such that you just take, you're not copying anything, and you're just taking this original matrix, and you're simply saying the limits of this, and I'm going to use this portion to be the smaller matrix. I'm going to use this square over here to be this matrix. So what I'm trying to basically convince you is that the division is, we're not going to take any time. It's going to take a constant amount of time because we're simply going to take the size of the matrix and we're going to define the element, the boundaries. Okay, it's not taking all you're doing is defining the boundaries. That doesn't depend on n. It's you simply have to divide the number n by 2. Okay, just like perhaps we did before earlier. So if you're convinced that the division of the problem is of constant time, now what about the recombination? When we're recombining the problem, so we've got this and we've got this, how much time is it going to take to recombine? Is that also constant, or does that depend on n? So you divided up the problem into smaller problems, okay? But we need to do some kind of a, the effort to, we've got these solutions to the smaller problem, but you can see that we do have to spend some time to recombine it. Why is that? Because we have to take the two AE and BG and we have to combine them together. Okay, so what's f of n? What's the complexity of f of n? Yeah, very good. So can I get your name? Connor. So Connor is suggesting that should be theta of n squared. I presume it's theta. I mean, generally, we're just using theta. People agree, disagree? Okay, so hopefully you got from my reaction that, yeah, I just favoring that. Yeah, so do you have a question, or you just agreeing or disagreeing? No? Okay, good. So so hopefully you should be able to see that the amount of time for f of n is actually theta of n squared. Okay, why is that? Because you do need to combine these two, and adding two matrices is going to be n squared. So it's going to take some function of n squared. Okay. So actually it's going to be n upon 2 squared, but still that's theta of n squared. Okay. So essentially what we've got as our recurrence relation is equal to 8. Okay. And yeah, so A is 8 and theta is n squared. Okay. And so you might have just looked at the next slide, and seen the solution, but can somebody tell me what the complexity is now based on any one of the 3 methods that you choose to apply? So which method would sort of come, seems to be easier? Master theorem, yeah. So let's apply the Master theorem. Do you want me to go back to it? But now you should just be able to think about it, right? Is the complexity of f of n, how does that compare with the n to the power log to the base b of a, okay, which is the watershed function. So what is the watershed function? F of n, we know, is now n squared. And what's the watershed function? N to the power 3. Yeah, because log to the base 2 of 8 happens to be 3. Okay. So we've got n cubed as the watershed function and n squared as the f of n. So which case would apply over here? Is f of n more complex, slower, equal, or greater to the watershed function? f of n is slower, so it would be the first case, okay? And if it's slower, then all of the work is actually, because f of n is slower, so f of n can be disregarded, and the complexity is simply going to be done all the way at the bottom. Okay, you can see that there's a really bushy tree, so all the work is being done right at the bottom of the tree. Okay, so you break it up into, get a real mess down here, but the complexity over there is given by simply given by this function, which is the watershed function, and that comes out to be theta of n cubed. Okay, so what have we achieved after all this effort? Doesn't look very good. Okay, so all this effort for nothing. I think reminds me of some Shakespeare's. Okay, so we haven't really solved this problem. Okay, and why did we put in all this effort? So why? Perhaps we just like to do a lot of work, but the question is, if we use this divide and conquer approach, can you come up with a way to actually reduce the complexity? Okay, so this sort of gives us a way of thinking about the problem, and it sort of says, well, I've been able to use the divide and conquer approach, okay, and now all I need to do is what? If I want to get a lower complexity than n cubed, then if you look at this recurrence relation, then how could we reduce the complexity? What could we do with this recurrence relation to be able to reduce the complexity? If somehow magically we could change parts of this equation, what would we change? Yes. Okay, so either we could reduce A or we could increase B. Very good. So now you're thinking. So now, what if we try to increase B? Go back to the original problem, and increasing B would mean that now, let's say, instead of dividing up into into n upon 2, we could do n upon 3, okay, or n upon 4, and so on. Okay, and increasing or decreasing A would mean what? Decreasing A would mean that we're decreasing this number 8. Okay, and so which do you think? What does your intuition say? Where do you think, which would be a better approach? Yes, gentlemen. Okay, so your intuition, can I get your name? Davis. So Davis is suggesting that it's probably easier to increase B rather than to reduce A, because A seems to be kind of fixed. You can't do much with A, and B is perhaps you could play around with B and try to reduce it to become n upon 3, and maybe that would make it easier. Okay. Well, people thought that it wasn't possible actually to reduce this, okay, for a long time. So mathematicians have been working for centuries on these problems, but it wasn't until I think somewhere in the middle of the last century that gentleman by the name of Strassen came along, and he found out that yes, you can change it. But he didn't go with Davis's approach. He went with his own approach because he had to make a breakthrough. And he said, well, you can actually reduce the number of multiplications. Okay. So I'm now giving you a hint. Do you think that you can actually reduce the number of matrix multiplications? Okay. So here we're assuming that the number of matrix multiplications is always the same. But does that always have to be true? And have you come across some algebraic equation that might give you an idea that you can maybe reduce the number of multiplications by increasing some other part, maybe increasing the number of additions? Okay, so can you remember some polynomial equation which actually can reduce the number of multiplications by increasing the number of additions? I mean, now think in different areas, right? You've been studying math in some courses, and now this is data structure. Well, this is sort of related to math, but think about, can you think of an equation where you've got maybe 2 multiplications and Go ahead. You had a suggestion. Come on, don't be shy. Okay, so think about an equation where you have two multiplications and you reduce that into one multiplication, but two additions. Okay, think about that as well. All right, so it'll come to you. All right. So and I'd like people, if you can think of that example, come back to me. Okay, but let's see how Strassen approached this problem. Okay, so basically said that think about this particular expression. AF plus BH can be written as, you know, a bunch of multiplications. And he's sort of playing around with these multiplications, and he's saying that, well, AF plus BH can be written as A times, you know, this, and it ultimately AF minus AH plus AH plus BH, and these two terms, you're left with the original equation, okay? But you've just re-expressed it in a different way, okay? And again, that might say, well, doesn't seem to make sense. Why would we want to do it this way, okay? You're still doing, you had two multiplications over here, you still have two multiplications, but you know, you've just expressed the equation slightly differently, okay? But that's, you know, that's how mathematicians do it. They spend, you know, sleepless nights working on these problems. And so Strassen figured out that here's what we can do, okay? So and he must have worked on it for a long time, I'm sure. So here's a method by which you can break up the problem into not 8 multiplications, but 7 multiplications, okay? And what are those 7 multiplications? But you've increased the number of additions, okay? So let's count the number of multiplications. So he's saying that I can express this part with the following 4 multiplications, okay? I've just seen that I can express this part. We saw this AF plus BH over here, AF plus BH, okay? And so I'm expressing AF plus BH as a product of 2 multiplications, okay? But you notice that now some of these multiplications are going to be reused, okay? So this particular multiplication, which is one multiplication, 2 additions, but 1 multiplication, and this is the second multiplication, this is the third multiplication, 4th, 5th, okay? But the 6th one is actually being reused, okay? So this is the 6th multiplication, and then the 7th one over here is again being reused, okay? And then this term over here, this guy is being reused as well. This chap over here is being reused as well. This guy is also being reused over here. Okay, and this is the only new part. So I've given different colors to them. So you can see that now, contrary to what your intuition and what Davis, I believe, had suggested, is that you don't seem to be able to reduce the number of multiplications. That seems to be fixed, but mathematicians have figured out a way to reduce the number of multiplications by actually increasing the number of additions, okay? So now you have a whole bunch of additions, and then you might say, well, you know, have you really achieved anything? Yes, remember, additions are theta of n squared, and multiplications are theta of n cubed, okay? So we are, in terms of the complexity of the problem, now what have we done? If you look back at your recurrence relation, okay? You've got A now down to 7, and B is still 2. We're still dividing it up into 2 parts, okay? And the additions, even though there's a bigger constant over here, all right? But again, we can neglect that simply because it has a complexity of n squared, which is smaller, okay? So as when you get larger and larger problems, larger and larger values of n, as n goes to infinity, you know, this problem is going to become, you know, f of n is going to become smaller. So can somebody now tell me what would be the complexity of T of n? Which method would you apply? Now it becomes almost obvious that the only method that can be applied where you have A and B and F of n is the master method. Okay. So again, if you apply the master method, what do you get? What's the watershed function? Log to the base B of A. And what is that? Log to the base 2 of 7. Can somebody just calculate that for me? 2.81. All right, so I've had that before. So you get 2.81, and voila, we have a solution. We've actually reduced the complexity from theta of n cubed to theta of 2.81. Okay, and this is when we clap Strassen because of his ingenuity. Okay, but interestingly, there have been a lot of solutions subsequent to Strassen. Okay, so people got the lead, and people who are trying to come up with a better method and want to publish a paper, maybe PhD students, professors, they said, well, why can't we actually try to reduce this? Okay, but there's a trade-off. Remember, if you try to make things less complex, there's always a trade-off. What's the trade-off? What's the trade-off? Yeah. Yeah. So definitely very good. Can I get your name? Sorry, T. So T is suggesting that, first of all, we haven't spoken about this much, but memory is also very important. Okay. So memory is one thing that is going to be, it's going to take up more memory, right? Because you have to take up the smaller matrices, and those have to be saved somewhere before you adding them up. Okay. So certainly seems to indicate more memory. Okay. What else? What is the other trade-off? So besides space? Yeah. More complicated to implement. Very good. Okay. So you're getting some great ideas. So that's another complexity. But I'm looking for the obvious, which was time complexity. Is that time complexity increased at all in any way? Remember, what have we traded off? We're doing less multiplications, but more additions. And additions, even though they're, in terms of the complexity, it's theta of n squared, but in real world, you have to compare real solutions. Okay, so you're not necessarily looking at when n goes to infinity, you're actually looking at real world problems, which n may not be infinite. Okay, and may not be extremely large. So if you're just looking at a 5 by 5 matrix or 10 by 10 matrix, is it really worth it to use this approach? Okay, or 16 by 16 matrix. Okay, so it only becomes useful when n becomes really large. Okay, so the trade-off is that you are having more additions. Okay, so the time complexity does increase to some point, but as n becomes really large, that comes out to be useful. Okay, so people did come up with better solutions, but the complexity for small values of n started to increase. Okay, and so the latest, there's a whole bunch of solutions, and if you look at the complexity, it's been going down. There's a Wikipedia page which actually tells you it's down to, like, I think 2.3 or something, or 2.37, something like that by now. And it's not, and there's been a whole bunch of solutions. Even Strassen himself improved it. But all of these problems, actually, the only problem which is perhaps used to some extent is Strassen's algorithm. The other algorithms had so many more additions and was so much more complex that it doesn't make sense, okay, to even use them in practical solutions. And they would only become useful when n is perhaps really large, okay? And real world problems, when n becomes really large, for example, 1,000 or 10,000, then you have other techniques, because generally then, if some of you have worked with matrix solutions, for example, solutions of linear equations and so on, then the matrix becomes sparse. And then you have better solutions for handling with sparse matrices. Okay, you have approximate solutions and so on. So this is a good theoretical problem to show you how divide and conquer works. And Strassen's solution is used to some extent, but it may not necessarily be the best way. Okay, and you'd be sort of hard pressed to actually see real algorithms or real implementations of even Strassen's algorithm. Okay, so some of them it's useful to know, but in real life you may not come across it again. Okay. All right. So how are we doing with time? So we do have a little bit of time. So that was essentially the end of chapter 4 of CLRS. Okay. So now we've done with divide and conquer. And we've sort of, again, to remind you that what we've looked at is we looked at 2 examples, merge sort, matrix multiplication, and we've seen proof of correctness for merge sort. We saw 3 different solutions, and then we applied the master method to an example of divide and conquer, which was Strassen's algorithm. Okay. So now let's go on to the next major topic, and this will be probabilistic analysis. Quite a change from what we've been talking about so far. And as I said, probabilistic analysis comes in very useful when you actually do want to have an average. Okay, if you want to figure out what is the mean complexity, and then it also comes in very useful when you have a whole different class of algorithms, which is called randomized algorithms. Okay. And randomized algorithms, just to give you a hint, does anybody know what a randomized algorithm is? Any clue? So we'll talk about it, but think about any one of the algorithms where, for example, we're doing sorting, okay? And in some of the cases, we said that the worst case happens when? The worst case is very unique, but happens in certain unique situations. Does anybody remember sorting algorithm where the worst case happens in a particular scenario? Yes? Okay. So you can think of different scenarios where it could be completely in the reverse, or in fact, it could actually be completely sorted. Okay, so you can think of algorithms in which those special cases are true. So what randomized algorithm says is that, and in a lot of real world scenarios, you actually get data which are already pre-sorted. Okay, and some of the algorithms may actually be the worst if you actually have a pre-sorted sequence. Okay, so what randomized algorithms say is that, well, let's try to take the original problem and we're going to randomize it. Okay, we're going to take that sequence, we're just going to convert it into a random sequence, because we know that actually randomized algorithms have a better on average complexity than some of the actual problems that we have. Okay, and it's just sort of giving you a taste of what's to come, and we'll see as we go forward. We'll take a look at this. Okay, so 2 different ways in which we're going to use probability. But to be able to use probability, first you have to remind yourself of what probability is. Yes. Yes, that could be. Remind me of what bogus sort was. Yeah, that was a really bad algorithm, if you ask me. Okay. I don't think so, honestly. Well, let me take that back. Okay, I'll have to think about that. But that's a good point. And maybe bogus sort. The algorithm itself was really bad, but partially the concept was correct. The sense that we randomizing it, but then we're using a real algorithm. Okay, not a bogus sort. Okay. So so let's take a look. So I'm going to take 5 minutes and try to jog your memory to see how much of probability do you remember. So how many of you have taken a probability course? Isn't that a prereq for this course? No? Okay. So anyway, so because it's not a prerequisite, unfortunately, so I will have to spend a little bit of time on probability, and it's not just a revision, it's actually going to cover some concepts which you may not have come across earlier. Okay, so I do understand that I do have a bit of a challenge in front of me. So for those of you who've taken probability, okay? All right, just calm down, folks. It's not that hard, okay? So work on those neural networks up there in your brain and try to recollect probability. Okay, so some questions. What is the sample space? Some definitions. It's a set of all possible outcomes. Okay. What are the outcomes? A simple example is doing a simple experiment. You're rolling a single die. Okay. What is S? What are the possible outcomes for rolling a single die? Sorry, 1 through 6. Yeah. So it's simply 1, 2, 3, 4, 5. Case is 6. If you roll 2 coins, okay, and each one of them can have head or tail, what's the total possible outcomes? 4. Yeah. And what are they? All of those combinations, right? Are these outcomes mutually exclusive? Yeah, people are nodding, right? So in any particular experiment, you would either have, if you're rolling a die, you either have one of those numbers. You can't have 1 and 2. Okay. You can't have if you're tossing 2. If you it's not rolling 2 coins, it's tossing 2. Okay. So if you toss 2 coins, then so if you toss 2 coins, then the result will either be an HH or an HT, but it can't be both. Okay, so you just have to be clear about that. So they are mutually exclusive. Yes. No, those are 2 separate outcomes. Okay, so you're doing an experiment which actually comprises of two tosses. Okay, that's one experiment. Okay, and that one experiment could either have HH or TT, and you can't have both. Okay, so what's the sum? Now, if you assign a probability outcomes, okay, what's the sum of the probabilities of all the possible outcomes? What should that be equal to? Should be equal to 1. And this is by definition of probability. Okay, so those are some of the basic axioms that we have in probability theory.